In the beginning, there was nothing. Then at time zero, about 12,000 million, the universe was born in a searing hot fireball called the Big Bang. In the earliest moments of the Big Bang, the stuff of the universe was unimaginably hot, a seething cauldron of electromagnetic radiation and microscopic particles. As the fireball expanded, the building blocks of all ordinary matter started to form. Atoms jammed together. Matter collected into clumps. From these clumps, the early stars were formed. Deep within them, the fury of nuclear fire began. Millions and millions of tons of hydrogen fused into helium. Energy burst outwards to form blazing suns. Stars smashed together. Stars exploded. Billions of stars moved towards common centers where gravity dominated their every move. They began to wheel about those centers to create the cities of stars, the galaxies. Still creation marched on. Material ejected by exploding stars settled into cold bodies, circling around newborns. This was the beginning of planets and moons. Just over 4,000 million years ago, around a very average star in a very insignificant part of the universe, our solar system was formed. This could all be science fiction. So why have scientists come to believe such a bizarre idea? The deep exploration of space allows us to see far back in space and time. The Hubble telescope is built to see 12,000 million miles across the universe. In many ways, it's like a time machine. This picture was taken by the Hubble telescope. It shows many distant stars and galaxies, but we're not seeing the universe as it is today. Astronomers believe it's a picture of the universe as it was 5,000 to 7,000 million years ago. Light travels at 186,000 miles a second. But even at this incredibly high speed, it will take light millions of years to reach our eyes from some of the far-flung corners of the universe. So many of these images are pictures of the universe as it existed before the Earth was formed. The deeper Hubble looks into space, the further back in time it sees, and the closer it approaches the events that followed the Big Bang, the very origin of the universe. The stars are the powerhouses of the universe. How they work and how they formed is crucial to understanding how the universe was born. The Sun is our nearest star. It holds the key to unraveling the secrets of all the stars.
The three reasons why we'd like to study the Sun are, firstly, its effects on the Earth. It affects us directly, so we want to understand that. There are huge explosions called solar flares that occur in the Sun's atmosphere that can send streams of highly energetic particles into space. And we see the aurora borealis, the aurora australis. Those are the more beautiful effects of these things. Secondly, it provides us with an atomic physics laboratory. We can see gases in the Sun's atmosphere that can't be recreated on Earth. And thirdly, it provides us a view, if you like, a window into the rest of the universe, because the Sun is a star and we can study the processes on that star. The Sun is a very hot ball of gas, and as with all hot objects, it radiates, it glows. And most of the radiation is in the form of visible light, the light that we can see.
We can learn a lot about the sun just from its visible light.
We can discover how the sun works by finding out what it's made of, and to do that we need to analyse the light. Now normally to analyse the light from a star you need a large telescope like this one at the University of London Observatory. Now the sun is far from being a faint star. In fact, it's so bright that if you were to look at it with your eyes, or goodness, a telescope like this, you'd certainly do a lot of damage. What we can do, because the sun is bright enough, is just point this telescope at the daylight sky, because there's plenty of sunlight around. Once we've collected that light, we can pass it through a variety of instruments, or something called a spectrograph, and that has in it either a grating or a prism, which will split up the white sunlight into lots of different colours, and then we can have a look at those to see what the sun's made of.
When ordinary white light passes through a prism, it's split up into its colours to produce a spectrum. If white light is passed through this special slide called a diffraction grating, a spectrum is produced again. If we look at neon light through a diffraction grating, we don't get a continuous spectrum. It's made up of lines. This line spectrum is neon's fingerprint. Other elements like hydrogen and helium have their own characteristic set of lines, which are different from neon's. We can identify all elements from their line spectra.
When we split the white light up from the sun, we find that it creates all these colours, and on top of these colours there seems to be numerous dark lines. These lines are like fingerprints, and they tell us what elements and molecules are in the sun. I can see a line near the red end of this spectrum which I know corresponds to hydrogen, so I know there's hydrogen in the sun. Over in the blue end of the spectrum I can see two very deep lines which I know are calcium lines. So we've got hydrogen and calcium in the sun, and numerous other lines which I know correspond to things like iron, silicon and oxygen. From information such as this, astronomers can tell that the sun is basically a very large ball of gas, mostly hydrogen.
Hydrogen is the simplest and most abundant element in the universe. It was the first element to be produced after the Big Bang. This can contains hydrogen. When ignited, a chemical reaction occurs with oxygen. Even though this is a violent reaction, it's not enough to explain how the sun works. But under certain conditions, hydrogen can cause a nuclear explosion. This is what we believe happens inside the sun. It's like millions and millions of hydrogen bombs exploding every second at the center of the sun.
The energy from the sun is derived from the hydrogen in the sun. The hydrogen is fused to form helium. We should think of the sun as a huge ball of gas. You could fit 1 million Earths inside that ball of gas. The surface temperature of that ball of gas is something like 6,000 degrees Celsius, and at the core it's a staggering 15 million degrees Celsius.
At these extremely high temperatures in the core of the sun, hydrogen nuclei join or fuse together to form helium. And during this fusion, an enormous amount of energy is released. It is this energy that powers the sun.
Eventually that hydrogen will run out, so the sun has a natural lifetime. It will die. It will have an end of life.
But how did the sun begin? Nearly 5,000 million years ago, in a spiral arm of our galaxy, a cloud of gas and dust existed. Young stars were created when part of the cloud started to collapse, forming a protostar. This is how our sun started life. As the gas and dust at the center of the cloud got squeezed together, it started to heat up. The temperature became so extreme that hydrogen started fusing to helium. The sun switched on. The remains of the gas and dust around the sun eventually formed the solar system. Our sun is currently at middle age, and luckily for us, it's stable. But in a few thousand million years, it'll run out of hydrogen in the center. As the energy from the hydrogen fusion reaction stops, the center of the sun will begin to shrink under gravity. Around the helium core, hydrogen continues to fuse. It causes the sun to swell up and form a huge red giant. As it swells, the sun will swallow up Mercury and Venus and leave the Earth parched. Eventually, the helium core becomes so hot that the helium starts fusing into, among other things, carbon. The sun now begins to pulsate until eventually, in one of these pulses, it throws out its layers, forming a planetary nebula. The center of the sun remains, a white hot core called a white dwarf. This slowly cools down, still orbited by the charred remains of the Earth and other planets. But how do we know that our sun will become a red giant and a white dwarf?
If an alien came to the Earth and found one human being and studied that human being, they'd be able to say something about how that person worked, how they breathed, how they could see, something about how their arms and legs worked and so on, but they wouldn't understand anything about the life cycle of human beings. In order to do that, they'd have to see babies, adults, older people, and then they'd know something about the life cycle, how people are born, how they die, and so on. Of course, astronomers are in the same position. We have this star called the Sun, which happens to be close to us. We can study it in great detail, we can understand something about how it works, but to look at the life cycle of the Sun, we really need to look out at the other stars, and we can see stars in different stages of their life in the same way as the people were in that analogy. So you see younger stars being formed in gas clouds, you see stars like the Sun, you see the old red giants. You see stars exploding.
Well, all stars, including our sun, are usually born somewhere like this, and there are stars forming in this cloud of gas and dust. Now, when we study this, we can see that there are stars that are about the same size as our sun, but there are many that are much, much bigger, and much bigger stars have a completely different life cycle. A big star, by being big, signs its own death warrant. Because it's so big, its nuclear reaction goes much, much faster, and it consumes itself in a much shorter time than a star like the sun. And what we can see here with this very large star is that it's already unstable. And so what's happening is you can see that there are these large amounts of gas here, and they are expanding outwards from the center of the star. And the fate for this star is to blow up in a dramatic way, and we call that a supernova. During a supernova, a star will almost outshine an entire galaxy. It gives off an awful lot of energy, and it basically blows itself to bits.
After it is blown up, a supernova ends up as a neutron star, or even a black hole.
We think that the universe was probably born in something we call the Big Bang, but it's not a bang in the sense of an explosion with bits flying out all over the place. It's more of an expansion, an inflation. We can describe it a bit like a balloon. You've got lots and lots of matter and energy, and then something happened, we don't know what, that made it inflate. And then the galaxies that we see in this picture are a bit like the dots on this balloon, and they're still expanding away from each other. And we can see that when we look out in the universe today.
So how do we know that the universe is expanding? We found out what was in the sun by looking at its spectrum. But the light from stars and galaxies tells us more than just what the stars are made of. It also tells us that they are moving away from us. This is the spectrum of a galaxy. It has lines like the sun. This is a spectrum of a near galaxy. It tells us that the element calcium is present. It's in black and white to make the lines show up better. This next spectrum of a galaxy that is further away from us also shows that calcium is present, but the calcium lines have moved. They should be here. And the third spectrum is from a galaxy that is even further away. Again, the calcium lines have moved further right. This is called red shift, because the lines have shifted towards the red end of the spectrum. So what causes red shift? Imagine an alien spaceship is traveling very fast. It's approaching the speed of light. As it travels towards us, it looks blue. As it travels away from us, it looks red. All objects traveling towards us at high speed look blue. All objects traveling away from us look red. So, if our calcium lines have moved to the red end of the spectrum, the galaxies must be moving away from us.
So the lines in the spectra of these galaxies are moving from the blue end of the spectrum towards the red end of the spectrum, this red shift. And if that's the case, the only way we know to explain that is that the space between these galaxies must be expanding. They must be moving apart. And this is evidence that indeed expanding and getting larger. Well, if it's expanding, does that mean that a long time ago it was much smaller than it is today? This noise is the cosmic background radiation. It's just a faint hiss now in the universe, but we think it's the echo of the unimaginable fireball that probably was the Big Bang. The Big Bang, this hiss left over, is probably the most conclusive piece of evidence we have that once upon a time the universe did start with this amazing cataclysm.
If the universe was born from an unimaginably hot, bright flash to create stars, galaxies and planets, the energy from the flash must still be around us. We can't see it, because after about 12,000 million years the light has dimmed. But we can detect it with radio telescopes. This signal is what is left over from the Big Bang, and this is a computer image of these signals. No other theory can explain this cosmic background radiation. And if the stars were formed in this cataclysmic explosion, the galaxies must still be expanding outwards at some phenomenal speed. Evidence for this comes from red shift. Objects traveling away from us look red. Light from very distant galaxies is red shifted.
At the moment, we cannot be 100% sure that the Big Bang actually did happen. All the evidence points to it, but the only way we'd ever know for sure would be to go back and witness it.
Who knows? The next generation of Hubble telescopes, built in the 21st century, may be able to look even further back in space and time, to witness the universe in its early throes of creation.